I'll have a short review in cosmology, but mostly I'll talk about the recent work, which is given here, and something which is work in progress. So there was no really good explanation of inflation of dark energy in field theory until recently. And from about 2003, some new ideas in field theory came up, and they were with regard to flux compactification and modular stabilization, which was also covered in Shannon's talk. And he used the application of these ideas to particle phenomenology. But simultaneously with these class of ideas, there was a concept of landscape of vacuum, and some of them are de Sitter vacuum, which was the need for understanding of dark energy. And the simplest example, simplest model was given by using such a Pauchinsky and Kachu and Radium of stabilization of volume of the internal fifth-dimensional space. Because string theory, the physical string theory, supersymmetric, is supposed to be fundamental in 10-dimensional space. On the other hand, all observations point out towards the picture of the perfectly 4-dimensional general relativity plus something. So I shortly remind here the basic steps in this construction, where we use work geometry of compactified space and some non-retardative effects, like either Gaussian condensation or instantaneous contribution. And this allows to fix some modular at anti-de Sitter space. And this is very bad because it has negative vacuum energy. However, we know plenty of them because there is a situation with unbroken supersymmetry and stabilized volume. So this was not known before. The combination of these factors that we use fluxes and non-retardative effects, which at the first stage allows us to get anti-de Sitter space, which are well known in string theory, but not useful for cosmology. Anyway, the next step was what Shannon was also explaining in his talk, that we had to, so this was the first stage where the stabilization of modular is performed with negative cosmological constant, and therefore we need to the stage of uplifting this anti-de Sitter space. And it turns out that to make it uplifted, we are ending up with something which is now understood as metastable de Sitter space. And the reason for this metastability comes from the following. So this contribution from either anti-DC grain or fluxes on G7 always has some inverse power of volume module. And therefore, we start with this curve, which gives us negative cosmological constant, and we add a curve. This is the sigma direction. It goes approximately like that. When we add those two curves, what becomes kind of known situation today, we find metastable de Sitter minimum. And this metastability comes because we have a dip here, and we have a curve which goes like that. And therefore, when we add them up, we have a nice positive cosmological constant where we drop the volume of S4 dimensions, but also we have a barrier which separates a fixed value of the modular from infinite sigma. Infinite sigma would mean that we'll have infinite volume of 6-dimensional space, and just string theory will go back to standard 10-dimensional picture, which is not what we observed. And therefore, this procedure of trapping the total volume of internal space is coming out together with this concept of metastability. So in principle, we can tunnel and the space will decompactify, but the variation of the time is huge, and in all practical respects, this is quite a nice positive cosmological constant. So with regard to dark energy, therefore, the the explanation which string theory has today is that at least there is some reasonable construction of metastable topological constant with equation of states which is W equals -1. And so far it is in agreement with all available data, and from all we know, in string theory there are no other comparing models. But fortunately, so far there is no disagreement. And so in the first day of the conference, I asked people who are looking for more data whether they will be able to tell us in a short time from now that they ruled out cosmological constant. So the answers which I hear are that probably we will just be able to say with better precision that most likely it will not be easy to rule it out. So for now, at least one explanation of dark energy is available. Now, since 2003, when these first models of modular stabilization were suggested, there were also several models of inflation constructed in string theory, and some of them have this nice value of spectral index, which is 0.95. And they typically predict low level of gravitational waves and low non-Gaussianity, and they may explain light cosmic strings if such will be found. And so the observation of gravity waves, cosmic strings, or non-Gaussianity can help us to test string theory. There are two types of string inflation models. One of them is modular inflation. So it is the simplest class of models, and they use only the fields that are already present in the generalized constructions. They don't need any brains. So we have our four-dimensional space, we have internal space, and we have modular which describe various shapes and sizes of internal space. Whereas if we work with brain inflation, the inflaton field corresponds often to the distance between brains and Calabi-Yau space. This class of models have been constructed with various properties, and I will give you just a picture of a short comment. So one of the kind of popular models, simply because it exists longer than other models, was constructed by Patrick, myself, in the Maldacino, Alistair, and Trivedi. And it is a brain anti-brain inflation in the work throat, which can be explained. And there are recent studies of these models. And the only comment I can give now is that in this model, it is kind of difficult to make a definite prediction, for example, for spectral index, which you can consider either as a negative point or as a positive one, because by the time after Planck we will know the value of spectral index better. Perhaps in this model we can find any one which will be close to experimental. There are various issues of fine-tuning which we need here, which goes back to the old problem of supergravity, that the mass of the inflaton could easily become proportional to h squared, and this kills inflation. There are some versions of this model, for example, the situation where the deeply brain originates between two throats and kind of uses this time before it decides to go in one of the throats, and this gives a better way of seeing inflation. Now this hybrid D3-D7 brain inflation, which is a stringy version of D-term inflation by Vali and Dimitri and Javier. And it was my favorite model until recently. However, the spectral index here is 98, which was the best value after W-1, but after the recent data, the spectral index moved approximately to 95. And it turns out to be not so easy to change from 98 to 95. On the other hand, we still have to wait for Planck and other experiments, and so it is not ruled out, but a bit tense. Now, with regard to the Dirac-Born impulse inflation, I have no picture. However, the most important feature here is a strong nonlinear dependence on quadratic derivative terms, and therefore it allows particular features which in the beginning there was a strong expectation that this model will supply us with gravity waves as well as non-Gaussianity. And I'll tell you more about it soon. Now I switch to racetrack inflation, which was the first working model of modular inflation, which we constructed in 2004, and few authors are here. And the picture is that is extremely simple. There is a superpotential, which is racetrack superpotential and some constant term which comes from fluxes. We have just the simplest scalar potential for the volume module and nothing else. And with some amount of fine-tuning, and we need the twisting term. And so what happens here, with some amount of fine-tuning, we were able to construct a potential which has an extremely flat saddle point. And so here we have eternal inflation, and eventually the system waterfalls into stable minima of the kind I discussed before. This model, however, is not quite realistic because, in fact, to work in string theory, we can't use just one complex modular. So we need at least two. And so the first realistic example was same group of people, but more recently. And this is one particular well-known construction in string theory, which was by those people who know those numbering may recognize it. So the model starts as a Calabi-Yau fold, which has two Taylor moduli and 272 complex structure moduli, and a particular symmetry allows to fix all of them but two, and there is a precise geometry in Calabi-Yau space, and those two are psi and phi here. They are fixed, and then the rest is just to deal with the Taylor modula. And again, the Taylor potential is rather simple, and superpotential is simple, and as a result, again, we need a fine-tuning, but here we will again say that because in string theory there is this landscape of possibilities, it is not impossible, and the corresponding analysis is numerical. It is a heavy numerical calculation, but in the end of the day, this is what we see for both of these models. They are extremely predictable, so not cosmic strings. If cosmic strings are detected, this model is one. NF is really in a nice place because this is the value which, as of today, is looking like the best one. And the model is very clear, no gravity waves. So if either cosmic strings or gravity waves are detected, this model is gone. On the other hand, if it is not, this is quite a nice model. There is another class of models which was discussed yesterday in Kiloda's talk. And here we have to add additional moduli. And one of them is called Taylor modular inflation, and then the other is more general trajectories in the same space. It's called roulette inflation. And it has less fine-tuning, but it has more moduli and more parameters, and has specific feature that it can produce very large volume of non-participation. And again, has a nice prediction of spectral index around 96, no gravity waves, and no cosmic strings. So there was recently a debate as to what can we say with regard to tensor modes in all these models. And the debate was between a number of people, mostly on email, and the conclusion is kind of here that all known brane inflation models, as well as modular inflation models in string theory, predict a non-detectable level of tensor mode. And this includes the known versions of GBI models. Now, there was a model of inflation which was suggested by a few people out here in this room. And this model is stringy version of assisted inflation. And the point which we all seem to agree that it still has to be derived from string theory. And I would like to also make a strong statement that this conclusion is with regards to already existing models where people did all the tests. However, we may expect new models or new version of known models, and they may lead to different results. But this we have to see before we trust it. Now, there are two important issues with regard to most crucial future data from cosmology, from astrophysics, and from particle physics. The first one is we would like to find inflationary models in string theory predicting the detectable level of D-modes or prove the no-go theorem, because eventually there will be a statement from observation. The other thing is that it would be important to relate inflationary models to particle physics, and the bridge goes through the mass of gravitina, and the reason is that there is a bound, which Linda explained slightly in his talk, and I'll repeat. And so the bound is, which says that there is a relation between the mass of gravitina and Hubble parameter during inflation, and this is with regard to models based on PQLK constructions. And therefore, if we know from particle physics or from dark matter searches or something that gravitina is in TV scale, this would mean that if we work in string inflation with this construction, it would mean TV scale H, which is somewhat unusual in cosmology, although we had a talk here about the standard model type inflation. So this has to be sorted out. The other situation, we have this large volume compactification model. We just recently agreed with Kiveta and collaborators that the corresponding bound is even stronger, that h squared has to be less than the gravitina squared divided by mu. And for example, which they recently considered, the TV gravitina requires mu of the order of 10 to 15, and therefore the Hubble constant in this class of models seem to be extremely small in case gravitina is in TV scale. So this situation is rather tense, and therefore I will also attract your attention to the fact that there are some models which are rather fine-tuned, where the bound is absent. And this is a model which was suggested by Andrei and myself, and I'll explain it later. So with regard to tensor modes and gravitina, the following can be said, that if they really measure, if they detect gravity waves, this would mean in Planck units we know what is the Hubble parameter on one side. And in the well-explored models of this type, we have this bound. So if the measurement of gravity waves tell us what is H, we have information on the gravitina mass. And the reason for the bound is that because we add this curve, which behaves as 1 over sigma squared or 1 over sigma cubed, any inflationary energy which we add will always lead to destabilization if it is too big. This is the reason for the bound. And this connects particle physics with cosmology. So the detection of gravity waves would mean the corresponding relation between R, the ratio of tensor to scalar modes, and the mass of gravitina. For example, if the detection goes at the level of 10 to the minus 2, which may happen not before 2020, it will, however, mean that the mass of gravitina in this class of model has to be extremely high, and perhaps Salas Dimopoulos will tell us something about it. It is not impossible, according to strict sufficiency. However, if we learn that the mass of gravitina is in TV, then the prediction of this class of model a completely undetectable level of gravity waves, because in fact R has to be 10 to the minus 24, and 10 to the minus 2 is something people expect in 15 years from now. So, however, in this situation, we have, if gravitina is light, and if we use the models which were well explored, where the height of the barrier is something which protects the volume of six dimension from become infinite, then it leads to extremely small H1 unless we use either this class of model, which were designed specifically to make the following, that the model has a minimum, a Minkowski, and the height of the barrier is completely independent on Hubble parameter. However, this model was not